Hello, everybody. Welcome to Classical Mechanics with Dr. TJ Hammond. This is for Monday, September 14th, and in this lecture, I'll be reviewing oscillations. So for today's lecture and Wednesday's lecture, we'll be talking about simple harmonic motion and oscillations. So one thing I forgot to talk about on Friday is office hours, so we'll be discussing this in class as well. But I meant to bring up when we should have office hours, so we can discuss this, and please let me know your preference. Okay, so why are we covering oscillations and simple harmonic motion? So one thing is I want us to remind ourselves about second order differential equations. So as you know from last year in intermediate mechanics, Newton's laws are second order differential equations. So F equals ma, or mx double dot, where that double dot or second order derivative of x with respect to time gives us a second order differential equation. The other thing with simple harmonic motion is that this introduced the idea of complex notation. So a lot of times when you have, Newton's laws or Newton 2, you solve for F equals ma or F equals mx double dot. But of course, these forces are real, the motion is real, and so everything involved will always be real. However, for oscillations, it's actually natural to use complex notation. And so I want us to remember why we use complex notation and how it's useful in this instance. Complex notation becomes extremely important for your third and fourth year classes, and especially grad school. So I want you to become more familiar with it here so that it helps you not just now, but also in your future career. We'll also be using oscillations as a simple model for describing, for using energy to describe the system. And this becomes very important next in a few weeks when we discover, or when we discuss Lagrangian and Hamiltonian mechanics, where instead of using forces and momenta, we use energy to describe the motion. And this also, because we won't be dealing with dissipative forces in this class, everything will be conservative, we'll have conservation of energy, and so we can discuss conservation of energy here. So for the daily assignment, read and summarize the beginning of chapter 3 from your textbook, so sections 3.1 and 3.2 for Wednesday. And you can post that on the daily assignment on the Blackboard. Okay, so for oscillations, we'll be dealing with forces that look mainly like something like this, where the f of x is equal to negative kx. So the reason why we're going to be using that is because that is going to be the first derivative in this Taylor series, right? So we take the Taylor series of this force, f of x, and the first term is just f naught, just some constant force. So obviously that isn't position dependent, so we often won't care about it. But then this first term will be x dependent. We have this x, and then that x is then multiplied by the derivative of f, evaluated at some point, and we'll typically be using x equals to 0. And so that means that if you think about simple harmonic motion, we have a force that is simply proportional to the displacement, so negative kx, and that is Hooke's law. And so oscillations will be basically the simplest case of this Taylor series. So the nice thing is that if we ever have some force, so as we talked about in the previous lecture, we have some potential that might look like this. Well, if you look at just this area, say here, what we get is something that looks parabolic. And so u will be proportional to x squared here. So I should say this is x direction, and this is our potential here, u. So if we have, or maybe I can draw that a little bit better. So if we have some potential that does something crazy and then has some minimum, well, this region here will look somewhat parabolic. And so if we're just kind of, say, zooming in on this region here, well, the potential is proportional to x squared. And if you remember how force and potential are related, we have that the force is equal to negative the potential, the derivative of the potential with respect to x. So if this is proportional to x squared, then that means that this is going to be proportional to negative x. And so for any potential that has some kind of minimum here, we can always approximate this as some kind of parabola near that minimum. And so this will be really, really common in a whole bunch of different problems. It's useful for orbits for electronic orbits. It's also useful for planetary orbits. We can also use this for molecules. We can use this for a whole bunch of different very common situations. And so to kind of get the first guess, we always kind of take this first simplest case of this Taylor series. And so that gives us this simple harmonic motion. So of course, this force is proportional to negative x, and this constant of proportionality is called the spring constant, which is k, where k is just going to be equal to the derivative of this force with respect to x. Okay. So simple harmonic motion, as we said, we have F equals ma, or F equals mx double dot. So that means that from Newton 2, mx double dot is equal to negative kx, right? So what we get then is we get an equation, mx double dot plus kx is equal to 0, and that's our second order differential equation. Often what we'll want to do is define this angular frequency of oscillation. And so we define this angular frequency as omega squared is equal to k over m. And so what that gives us then is x double dot plus omega naught squared times x is equal to 0. Okay, or what we can think of this as is d squared by dt squared of x plus omega naught squared x is equal to 0. All right, so that's our second order differential equation that describes harmonic motion. All right, does that make sense? We've shown that if we ever have a minimum in a potential, then we can approximate that as some kind of simple harmonic motion. From Newtonian mechanics, we see that this second order differential equation, this F equals ma, is going to be proportional to this displacement x. And so that gives us our second order differential equation. Okay. So, as I said, the equation of motion is going to be a second order homogeneous differential equation. So what makes it homogeneous? It's that what we have is x double dot plus omega naught squared x is equal to 0. It's the fact that there's a 0 on the right-hand side that makes this homogeneous. So this isn't necessarily true. We could have a driven harmonic oscillation. And so maybe I'll use a different colored pen. So if we had a driven case, we could have x double dot plus omega naught squared x is equal to some f, say, of t. So that's some time varying force. So it could be that we have a spring, some mass on a spring, and then that spring we're hitting it every once in a while or something like that. Or what you'll see in electricity and magnetism is you'll have an electron in an electric field, and so this electron will be oscillating in this electric field, and this field is driving this electronic motion. So there are many, many instances of this driven harmonic motion, but having something on the hand side here that isn't dependent on x makes this an inhomogeneous differential equation, and these are harder to solve. Often it's easy to solve these numerically rather than analytically. There are, of course, analytic solutions, but that might be for like the steady state or something like that. Okay, so one thing I really want to emphasize is that there are two orthogonal solutions to this. So because this is a second order differential equation, there have to be two solutions. This is a mathematical property, but it's also a physical property. Mathematically, it's required. Basically, if you have a first order differential equation, like say a decaying exponential or something like that, you can have one solution, but you have a second order differential equation, so you must have two solutions. So how you might have solved this in, say, differential equations is you would have a trial solution. And so you might think of, some e to the pt or something like that. And then you have, say, x of t. Oops, maybe I'll go back to the black pen. You have x of t, and you'll have this trial solution, and you'll say it's e to the pt, and so x dot is going to be p e to the pt, and so x double dot is equal to p squared e to the pt, and that's going to be p squared times x. And you say, oh, well, this is x double dot is equal to p squared x, and what I had was x double dot is equal to minus omega naught squared x. So what that means is p squared is equal to negative omega naught squared, or p is going to be plus or minus I omega naught. You might have seen something like that in differential equations. And so you can use that by trial solutions. I'll get a little bit, in the next slide, I'll show a little bit more why that trial solution works. I'll also ask you, what other forms can this solution take? You're probably used to seeing cosine and sine, and we'll get into how these are the same thing. By the way, I mentioned this before, but I'm going to emphasize this again here. This course does not deal with dissipative forces. So in chapter 3, they get into dissipative forces. In intermediate mechanics, we also dealt with dissipative forces and dissipative systems. We're just not going to do that in this course. The main reason for that is that Lagrange Hamiltonian mechanics become more complicated if we start to deal with loss of energy of non-conservative systems. And so in order to just kind of keep things simple, since we're introducing this new idea of Lagrangian mechanics, we're just going to say none of those cases are dissipative, and then all the examples after that are not dissipative either. And so I'm just not going to deal with dissipation in harmonic motion either, or oscillations. Okay, so I asked, where does this trial solution come from? So what we can say is that we have this differential operator, and I guess I could write this a little bit more clear, that this differential operator, we'll just call capital D, is going to be d by dt, okay? So when we have this x double dot plus omega naught squared x is equal to 0, that is going to be the same thing as writing this big D squared times x plus omega naught squared times x equals 0. Well, that is a quadratic equation which has the solutions d plus I omega naught and d minus I omega naught. And so it just doesn't have, it has two roots, but no real roots. So they're both complex roots or imaginary roots. So we set one of these to 0, and so I'll set, and so anyways, I set one of them to 0, and so I have d minus I omega naught x is equal to 0. But don't forget, d is actually standing in for this differential operator d by dt. So we have d by dt of x is equal to I omega naught x. And so that means that we can bring, or I guess in the next one I explain a little bit more clearly. But this gives us a solution of x1 is equal to a plus e to the I omega t, where a plus just stands for, it's some amplitude a, and we're giving it to the positive root here because this is plus I omega naught t. I also do it for the other root, and this one is maybe a little bit more in depth. So the other root is d plus I omega naught x is equal to 0, and so that means that this differential operator d by dt of x is equal to negative I omega naught x. And so you bring the x over to the one side, and so we say it's dx by x is equal to I omega naught dt. So we have dx divided by x is equal to negative I omega naught dt. And then we just integrate that. And so we say the integral of dx over x is equal to negative I omega naught dt. Now, I told you in the previous class on Friday, if you can, always use definite integrals. Here, we don't actually know any of our limits. We don't know what we're integrating from for x. We don't know what we're integrating from for t. So I'm going to say I don't know any of these, and this will just give us an indefinite integral, which means that we have the integral of dx over x is log of x, natural log of x, of course. And so the integral of dt is just going to be t, so that gives us negative I omega naught t plus some unknown constant. We'll call it c2. So x2 is going to be, so we take the exponential of everything, so that's x2 is equal to e to the minus I omega naught t plus c2. But that can also be written as e to the minus I omega naught t times e to the c2. And so if we just convert this a minus is equal to e to the c2, then this is equal to a minus e to the minus I omega naught t. So we have two solutions because we had two roots in our second order differential equation. And so that means we have x of t is equal to a e to the I omega naught t with a plus and a minus e to the minus I omega naught t. So where a plus and a minus are not necessarily the same thing, but they will have to be complex. Okay? So that is where that comes from. So that gives us that's just a kind of a refresher of complex notation and why we can use complex notation to represent something, even though, of course, this has to be real. So the simplest solution, though, is, of course, x of t is equal to a cos omega naught t minus phi. This is probably what you saw in, say, first-year mechanics, where phi is determined by this initial conditions in some initial phase. And so what you have is this thing is oscillating up and down. This x of t. It's oscillating with some amplitude here. And it has some periodicity, say here, where it's going to be 2 pi over omega naught. And it starts out at this maximum point at some phase phi, which is given by these initial conditions. And so you say, oh, wait, but you had just emphasized that this has to have two orthogonal solutions. How do we get two orthogonal solutions from something that obviously only has one solution? Well, if you remember your trig identity, you have cos of alpha minus beta is equal to cos alpha cos beta plus sine alpha sine beta. And so what that means is that if you actually substitute that in, you get x of t is equal to a cos omega t minus phi, gives you a cos omega naught t times cos phi, a sine omega naught t sine phi. And so you rearrange that, so you get a cos phi cos omega naught t plus a sine phi sine omega naught t. And you can realize that a can be anything and phi can be anything. And so you can make a cos phi is equal to a1 and a sine phi is equal to a2. And of course, you can set your phi to whatever you want. So these things are completely separable and independent of one another. And so you get a1 cos omega naught t plus a2 sine omega naught t. And so that actually gives you two orthogonal solutions, since cosine and sine are completely orthogonal to one another. Okay, so let's go on to an example of simple harmonic motion. So what we have here on the left is simple harmonic motion of a pendulum. So you have some mass on the end of a string. That string is, of course, a fixed length, and this thing is swinging back and forth. And you've released it from some small angle, and it swings due to the force of gravity, and it has a restoring force that's proportional to the sine of the angle, theta. Okay, so let's think about this in terms of radial acceleration. So we went over radial acceleration when we were dealing with acceleration and velocity in polar coordinates. So if you remember, the acceleration in radial and polar coordinates will have a radial part. So it has this radial part here, and this r double dot is telling you how much, if this mass is accelerating away or accelerating towards this fixed point, the center point. You have r theta dot squared, and this is centripetal acceleration. So this is something you're familiar with. You've been seeing this probably since high school. Both of these are in the radial direction, okay? So if you have something that's orbiting around the other thing, like this, then it's that force that's pulling that other thing together. So you could either have this as gravity, or if you have this on a string, this is the strength of that string, or the acceleration due to that string. You also have acceleration in the theta direction, so in this tangential direction, and so you can have r theta double dot. So that's if you have something that's going around and accelerating faster and faster that way. And then you also have the Coriolis acceleration, which is proportional to both the velocity in the radial direction and the velocity in this angular direction. But we have the length of the string is fixed, so r dot will be 0, so the velocity in that radial direction will be 0, and also the acceleration in that direction will be 0. So this guy will be 0, and this guy will be 0. Okay, so from Newton 2, we have the radial direction of the force, so these are orthogonal directions, right? R hat is orthogonal to theta hat, just like x is orthogonal to y. So the force in the radial direction will give us the mass times the radius times theta dot squared, and that is going to be equal to the mass of this, the force due to the mass, or the weight. So this thing here, minus tension. But of course, this isn't in the same direction as the string, which is going out here, and so this is going to be the cosine component of it. Okay, so that means that this tells us what the tension of the string is, so that's going to be equal to mg cosine theta plus mr theta dot squared. So just a simple question, when is the tension in the string maximum? Of course, you know what this answer is, but you can kind of think about when that's going to be maximum. You can show that that's going to be the case from this tension equation. You also have the force in the tangential direction, so f theta. And so the term that's remaining in f theta is, of course, r theta double dot. And so you have the mass times r theta double dot is going to be negative mg sine theta. And so that is this component here, that this is a horizontal component along here. And so this component is going to be mg minus mg sine theta, right? So theta, if this is positive direction, this is in the negative theta direction, so that's why there's a minus sign. It's going to be proportional to the mass, of course, also proportional to gravity, and it's proportional to the sine of that angle, okay? And so that means that the masses cancel, and we get r theta double dot is going to be equal to negative g sine theta, all right? So that doesn't exactly look like our simple harmonic motion from before. So let's remind ourselves, what happens if we just move this a small amount? What if theta is quite small? So something like this, something like, say, 10 degrees or so. So let's Taylor expand sine theta about theta is equal to 0. We can call this a Taylor expansion. It's actually a Maclaurin series. If you remember that a Maclaurin series is a Taylor series just about that value, that variable being near 0. So if you remember what that is, we have, as I showed before, for a Taylor series, now we just have it for a Maclaurin series, so it's just at x is equal to 0, that our f of x is going to be f evaluated at 0 plus x times the first derivative of f. So if you remember, f prime is equal to d by x of f. Plus x squared over 2 factorial times the second derivative of f evaluated at 0 plus x cubed times the third derivative of f evaluated at 0 divided by 3 factorial, and this goes on and on and on for an infinite series. So what is our actual f of x? Our f of x is sine x, so that f evaluated at 0 is, of course, 0, since sine 0 is 0. Then the first derivative of f is going to be cosine x. So cosine at 0 is 1. Now we have the second derivative of sine is going to be negative sine, and so of course we have sine of 0. Negative sine of 0 is still 0. Then we have the third derivative is now negative cosine x, evaluated at 0 is negative cosine of 0 is negative 1. And this goes on, the fourth one is 0, the fifth one is positive 1. And so our f of x in this Maclaurin series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And so, you know, plus whatever. What's the next term? Yeah, I'm sure you can do this in your head. This will actually be minus x to the 7 over 7 factorial. And then you'd actually have a plus. So that should technically be minus sign there, but it doesn't really matter. And so if you think about it, if x is, say, small, say if it's 0.1, then if, say, x is equal to 0.1, then that means that x cubed is equal to 10 to the minus 3, and it's actually over 3 factorial, which is over 6. So it's much, much smaller, right? So that's why if we take it for small x, then this is actually quite small. Of course, if x is really large, then those higher order terms actually become even bigger. So we're just going to say for small values of theta, and so we're going to say it's for some value of theta that's like 0.1. And this is, of course, in radians, not in degrees. And so I can't remember. I think 0.1 is something like 10 degrees or something like that. But you can check that on your own. So if we approximate this for a small angle, we have theta double dot plus g over r sine theta is going to be equal to approximately theta double dot plus g over r times theta is equal to 0. And that's the exact same equation of simple harmonic motion, but instead we're replacing this omega naught squared. Instead of being k over m, it's going to be g over r. Okay, so here's a little animation of swinging pendulum. So blue, we have a simple harmonic motion that has a 10-degree starting point. In red, we have a simple harmonic motion, a pendulum swinging when it's at 55 degrees. And then in black, we have simple harmonic motion. When you see the notes, you'll see that it's smoother. For some reason, there's a bit of a lag in this, I guess. But you can see that the blue and the black follow each other quite well, whereas the red, after something like 15 seconds or so, they actually get quite out of sync. And so that means that the blue, for something that has about 10 degrees starting angle, it follows simple harmonic motion fairly well. Okay, here's another example. So we'll deal with a physical pendulum. So instead of just having simple harmonic motion, we'll actually deal with something that has, some dimensions to it. So if you have this mass here, so we have the center of this mass is located there, but the pivot for this is located over here. And so the distance from the center of this mass, from the center of the sphere to this pivot, is going to be r, or that's the radius of the sphere. The total mass of the sphere is m. And so this thing has a rotational inertia I, right? So for a sphere, about its center is 2/5 mr squared, okay? Now there's this thing called parallel axis theorem. You should be familiar with this. I think I brought this up in intermediate mechanics. In fact, I know that I did, but it might have you might have forgotten about it. There's this thing called parallel axis theorem. And basically what that tells us is if you have some object here, and you have it from here, and this has a radius, say r, and this has a radius r, then the total angular momentum, total, is going to be the moment of inertia of this plus the moment of inertia from this guy. So we'll call this orbital, and we'll call this intrinsic. And so it would be I orbital plus I intrinsic. Okay, so what we have is, of course, for the orbital part, all the mass is concentrated, say, in the center, and so it has this distance r, and so that gives us this moment of inertia here, mr squared. And then, of course, because this is a sphere, what we have is the moment of inertia here is 2/5 mr squared, if you recall that. So that means the total moment of inertia of this sphere pivoting about this point on the surface of the sphere is 7/5 mr squared. Okay. Now, if you remember from what we were talking about on Friday or from intermediate mechanics, we have a torque on well, torque in general is going to be r cross f. So r being this radius, and then the cross product with this force. But it's also going to be the moment of inertia times this angular acceleration, theta double dot. And so what we get is mgr sine theta, so just the same thing that we had before for our mass on a string, so mgr sine theta as the restoring force is equal to, oh, this should be minus sign, is equal to 7/5, yeah, this should have minus sign too, 7/5 mr squared theta double dot, right? Or theta double dot is going to be minus 5/7 g over r sine theta. And so for small oscillations, we say that the sine theta becomes theta again, and so our omega naught squared is 5/7 g over r. So compare that to our simple pendulum that we had before, that we had that the frequency squared was g over r. Now we have for physical pendulum, for when it's a sphere on the edge, when it's pivoting about its edge, that we get 5/7 times g over r. Okay, and so now we come to the end of the slides. Talking about energy in simple harmonic motion, this is a good example of how to visualize stuff with energy. It's so common and pervasive that it's really good to see this as early as possible. The kinetic energy is always going to be 1/2 mv squared, of course, or 1/2 mx dot squared. Now, since we have x is going to be a cos omega naught t minus phi, then that means that x dot is going to be minus a omega naught sine omega naught t minus phi. So we just substitute that into our kinetic energy, and we say t is equal to 1/2 m omega naught squared, a squared, and then sine squared omega naught t minus phi. Now we also get the potential energy, and just a note on how this is written. This I would actually to write as sine squared omega naught t minus phi. But for some reason, I couldn't get that to work in PowerPoint, but that's what I mean by that. And you'll see the same thing here with cosine, that it's actually that I would like that thing to be written there. Okay. So for the potential energy, we have the potential energy is going to be integrated from x equals 0. So that's from this point up. We have to integrate it from some point, so we might as well set it to the minimum. So we'll set it at where x is equal to 0. So we're integrating from 0 to x of fx prime dx prime. And the reason why we have these primes is because we already have x. So if we have x in the limits, we can't have x in the function, so we call it dx prime and x prime. Okay, oh, and speaking of, then that should mean that this is primed when this is primed. So that means that we're integrating 1/2, or m omega naught squared x prime dx prime from 0 to x, which gives us 1/2 m omega naught squared x squared. And so what that is 1/2 m omega naught squared a squared times cosine squared of omega naught t minus phi. But since you know how we can you know your trig identities. If you add t plus u together, what you get is 1/2 m omega naught squared a squared, and then of course you get cosine squared plus sine squared, where cosine squared plus sine squared will always give you 1. So what you get is the total energy of the system is 1/2 m omega naught squared a squared. Yeah, that's right. So what that means is that energy here is always going to be 1/2 m omega naught squared a squared. So omega naught depends on the frequency of this oscillation. A depends on your initial amplitude of this oscillation. But basically, this line here will always be same as long as there's no dissipation in this. And as I said, we're not dealing with dissipative forces. So the energy is always going to be the same. And this object is going to be, say, starting at some point. We're going to move it up to here and then release it. And this thing will oscillate back and forth, where it'll oscillate on this potential energy curve. And the reason why we like looking at that is because it's kind of like a ball oscillating in a bowl. So if you had this ball oscillating in a bowl, it would just oscillate back and forth and back and forth. So it's an easy way to visualize this by thinking about this in terms of energy, as opposed to force, which is like a restoring force that you have to think of, okay, more in the x direction, we have a stronger restoring force, and the negative, we have this negative k times x, and then if you go in negative x, this thing is stronger in the positive x direction. This is kind of an easy way to think about it, because you just kind of visualize this bowl, and then you have like a ball or some block that's oscillating back and forth in this bowl, and that's following that potential energy curve. And so, of course, the total energy is always constant, and the kinetic energy is just going to be that total energy minus that potential energy. So when you're at these extreme points, so say here and here, your kinetic energy will be 0. And when you're at the minimum potential energy, of course, the kinetic energy is maximum. So we'll be using this idea a lot in this course. So I'm introducing this concept here of discussing this in terms of energies. But as I said, we'll be dealing with this quite often for Lagrangian and Hamiltonian dynamics. All right, and that is it for the lecture on Monday, September 14th. I will see you in class.